Okay, so last time we introduced the basic theorem, and according to the basic theorem, if we apply a sine wave at the exit, and if we measure the magnitude ratio, in other words, we apply a sine wave at the exit, at the entrance, or at the inlet, at the control variable side. So if we apply a sine wave here, and if we measure that response to that, so here's the response out here. So when we measure that response, then of course we can always calculate a magnitude ratio. So the ratio of the amplitudes here, that's our magnitude ratio. And we can also look at the phase shift. So what's the difference with respect to the time in the heights here, for example? That's one way to get it. So basically we look at how the two curves are shifted with respect to each other, and that turns out to be the same as the angle of g of I omega. So this is all practical. We can measure this. That happens to give us g, the values of the transfer function at specifically s equals I omega. And what we want to cover today is why this matters. Why does it matter to us that s equals I omega? Why is that such a special thing to know? Because up to now, we've been talking about g of s. We've been deriving the transfer function as a function of s. And so that was nice in general. We knew that whatever s value our process was exhibiting, we could use that and we could work out g. And in fact, in almost all cases, the values of s that we were interested in were not imaginary numbers. There were no I omega type variables. So if you think of the poles that we looked at, the poles were something like -2, -3, -4, or 2, 3, and 4, and so on. So those s values were never imaginary, whereas now we are claiming to be interested specifically in imaginary numbers. So yes, it's nice that we can measure this, but why does it matter that we are so thrilled about having this result? So that's what we want to establish now. And I realize you might need a bit more experience with this proof, so we can come back, and if you have any more questions on the proof of this, we can go through this again. But for the time being, let's just accept that this is true, and we'll proceed from there. So you'll see there's a bunch of stuff after that proof. The Bode diagram and so on is introduced, and the Nichols chart and the Nyquist plot. So those are always visualizing things, and we actually don't need those right now. So we are going to skip past all that, and we'll come back to that after we've established what we want to establish here. So what we want to establish today is, it starts here where it says Nyquist stability criterion, right? And it starts here. We know that 1 plus g open loop. So in other words, the roots of this equation, those are the poles of the closed loop equation. And so those s values give us the time constants, and so we can use that to infer stability. So that's fine. Let's just park that result for now. We want to look now at this so-called principle of the argument. So the principle of the argument says that if we have z zeros and p poles of some function, then if we observe how our function behaves on some contour that encloses those, then the number of encirclements that we observe will equal z minus p. So just to explain that, right, that sounds quite mysterious what we just said there. So let's say we have some transfer function. So in fact, let's just do it this way. So we've got some transfer function. Let's just say g. And this g function has this form. So this g function, and we're not bothered about whether it's open loop or closed loop or something else. So we'll just say g has let's say there's a 0 here, and let's say there's a pole here. And that's in another pole. So okay, so let's say this is our function, the function that we are interested in. And we can see this function goes to 0 when s equals z1. So that's 1, 0. And then g goes off to infinity when s equals p1 or when s equals p2. So that's when g goes to infinity. So those are poles. And so those are different s values. So two sets of special s values. So if we look in the s plane, let's just draw those values out. Right, so this is our s plane. S plane. It's too big. Okay, so we're looking at the s plane here, and we are saying that there is 1, 0. And I'm just going to sketch something here. So there's 1, 0 and 2 poles. And let's just say they are sitting somewhere like this, right? So the one blue cross is a 0, and the 2 red crosses are the 2 poles. And when we move in the s plane, so let's just say we happen to be interested in this sequence of values in s, right? So we are looking at what's happening when we choose s values like this. And so these s values might be, let's just write them out here. Maybe this is something like 10 plus I8, for instance. So that's 1 point there. And if we, so let's just kind of identify a couple of points here. So there's another point there, and there's another point there. So at all these points, we have these different values. So maybe this, here's another point. So this is pretty much on 10 as well. And we can see the imaginary number is a bit lower. So let's say this is I7. And then you've got yet another point here. The x value is a bit bigger. So this is something like 11 plus. And again, the imaginary number is a bit lower. So that's I6. So those are different s values. And what will happen is, as we vary those s values, then g will go through some other values. So for each of those, and maybe we want to label them as well. So we'll just put here. Okay, so this is 0.1, and this is 0.2. And this is 0.3. So as we apply these different s values in our g function, so coming back here, we've got a g function. The z's and p's are fixed numbers, right? Those z's and p's are these fixed values here. Those are s numbers. So those are constant, those are complex, but those are constants, the z's and p's. And now we are looking at a couple of different s values. So if we stick in the first s value, 10 plus I8, then everything is specified, and we will get some complex number by the end of the day. And we might have to multiply by an I squared or something like that to get the imaginary out of the denominator, whatever. But by the end of the day, we can see g is going to be some complex number that we can easily get from that. So we can say then that on the g plane, there's something else. So here's the g plane. G plane. So G plane, which is G plane. And so we've got some other numbers here. And so let's say what? So let's say the first point turned out to be here, and then the next point turned out to be there. And if we took enough, instead of just 3 points, if we took more points, maybe we found that our G function did something like this, right? So, and these were the points as we defined them here. So this was point 1, and this was point 2, point 3. Right, so maybe to some of you, I'm really belaboring the point here, but I'm just emphasizing that when we draw things in the S-plane, right, we have to be clear about what the S-plane is and the G-plane is, because these are complex numbers. So we have to keep track of their real parts and imaginary parts. So as we choose points in the S-plane, then that will also cause something to happen in the G-plane as well. Okay, so that's one thing. Now, in our G-plane, we can imagine, you can imagine a surface that's sitting above the G-plane. So when we get close to this value, let's actually just copy it on. So when we look at the values of S at these points, then we can imagine on the G-plane, you can imagine a 0 here. So if you imagine the values close by this 0, that means all the G values are going down to 0 over there. So G goes down to 0 at this point. And then at this point, this is on the plane, and G is going off to infinity there. So that's what's happening. That's in terms of the magnitude of G, and of course G is an imaginary number. So yeah, it's that's giving you an idea about the magnitude of G, but the angle of G is also doing something else. So on the G-plane, we are getting a different, how can I say, we are seeing a different representation there. So on the G-plane, near this point, you will end up close to here. So the equivalent point on the G-plane is here, right? Your 0, if the S value, if this S value is a 0, then on the G-plane, we are going to be sitting here on 0. And then if these are poles, then for those S values, G is going to be off at infinity. And you can imagine a circle that goes around here, oops, where the radius of the circle is pointing at infinity. So G is somewhere out on infinity, and it's at some angle. So it will be some point on this infinite circle there. Okay, so this is all just to get us comfortable with the idea that as we choose points in the S-plane, and it's a plane because of real parts and imaginary parts, that there will be some other response on the G-plane, right? So that's one thing we can say. And I'm just going to clear all this. And now let's imagine back in the S-plane that if we pick a contour that applies here. So let's say we pick a contour that looks like this. Right, and let's say we are moving around the contour, and let's say we pick a starting point here, and we just move around this contour here. So as we travel around this contour, it's too warm here, 1 second. So as we travel around that contour, we can imagine that G is going to be doing something over here. Something is going to be going on in G. And we don't know exactly without actually substituting the numbers in and actually working out the complex values each time. And we don't want to have to do that. So what we'll try to do is imagine how the angle, let's just think about the angle of G, how that's going to change as we travel around this contour. So we would like to know how does the angle of G, right? Remember, we've got some function G here. And if we were to look at different values on G, so let's say as we are traveling around the S contour, as we've chosen to travel around it, that the G values are also going through some changes as well. So we can say then that at the starting value, that the angle here, it's this angle. So that's our starting. And then, in fact, let's pick a couple of points. So yeah, again, if we take, let's say 1 point here, so we take 1 point here, and then we take another point there, and another point there. And let's say we go ahead and we identify those points on G. So let's say that that's our starting point, that's the one. And then there's the second one, and there's the third one. Then we can see here the angle is going from a large value to a smaller value. So the angle started out here, right? Because that was 0.1, this one. And then when we went to the next point, that's at a lower angle. And then the last point is at an even lower angle. So we can see that G's angle is going down like this. So we are interested in how the angle of G is changing as we travel around this contour. And so we can do it this way. We can work through each of the values of G. But another way to do it is to think about the poles and the zeros here. So what we can say is, well, if that's our function for G, then the angle of G, so the arg of G, the angle of G is going to be arg of S minus Z1 minus the angle of S minus P1 minus the angle of S minus P2, right? And if you look back at your maths notes, you'll see that that all comes from Euler's formula, right? That the angle of a complex number can be obtained if we write it as a ratio of two functions that's equal to the angle of the numerator minus the angle of the denominator, and we can split the denominator. Remember that a complex number can be written in the form A, so if there's some complex number, it's S equals S naught E to the, let's write it this way, E to the E raised to the power A plus IB. So a complex number can be written in this form. In fact, we don't need the S naught because E to the A will take care of the constant in front. So any complex number can be written in this form. So we can imagine here E to the S plus Z1 E, and in the denominator E is here. So all these E's, when we multiply them together, their arguments will be added together. So that's why this works. Okay. Any questions on that? Okay, so if this is true, that we can say that the argument of the result is equal to the argument of the numerator minus the arguments of the denominators, if that is generally true, then all we need to do is look at each of the points in turn. So for instance, if we look at the Z point here, so we could say, well, near the Z point, if we are picking points, so again, we will pick a couple of points around here. So pick a point here, pick a point there, pick a point there. We can see that these Z values are going to go through. Sorry, in the chat you're saying, I'm only seeing what you're typing. The screen is stuck on Paint app. Oh, so when I Alt tab here, tell me, can you see the Word document that's on the screen right now? Maybe thumbs up if you can see. I know on some PCs, your lag time might be, you might have a lag on in your connection and it doesn't show the most updated. Thumbs up, everyone, if you can see the Word document right now. Okay, so it seems like, so I think that's on your side, your internet connection, but I will be YouTubing this video. So if it's lagging too much for you, then follow with the video as well, right? Okay, so just following this, the single zero here, we can see that as we travel around this contour, this angle is going to increase and it's going to come back to this point. So imagine here, we are picking points. We started here, the angle was on 0, then we went up here, the angle increased. And so each time we pick a new point on the contour, then we look back at the 0 and we can see the angle has increased by that much. And so as we travel around this contour, as long as this point, the point that we are looking at, as long as that point is sitting inside of the contour, then this angle will increase by a full circle, right? It will increase by 2 pi. And so we can say then that the function g is going to increase by a plus 2 pi for every 0 that we have sitting inside here. Because if we had another 0 here, then we could do the same thing. We could say as we travel around here, then this angle, it started at 0, then it went to this value, then it went to this value, and so it went through all the values. So its angle increased by 2 pi as we traveled around this contour. So every time we have another 0, the angle of g is going to increase by 2 pi, right? A complete rotation. So let's just get rid of this one. Right. So we can say that every 0 of g will increase the, well, one more thing we should say, every 0 of g in the contour, and let's call our contour, I don't know, C, right? So let's label our contour here. So we are calling this contour C, because this is something of an arbitrary choice right now. We've just chosen any contour C. So as long as every 0, as long as the 0 of g is inside of C, then that will increase the angle of g by 2 pi. It will increase the angle of g by 2 pi when we travel around C. Okay, so we are traveling around C here. So C is nice and defined. We've defined a contour C on the S-plane. And as we travel around C, we know that G, something is happening in G. So G is doing something here. So G is, maybe G is doing this. So G will do this for every time we orbit that 0. So that's what happens on the 0 side. Now the poles are, of course, in the denominator, and it's minus in this case. So it's S minus P1. So we can see here that if we do the same exercise for each of these poles, so let's say we start here. So this pole, it starts on 0, then we choose the next value. So we travel along here, then the angle here has risen to this value. And as we go all the way around, then this pole, its angle increases also by 2 pi. So, and this pole will also contribute 2 pi. So as long as it's sitting inside, then the angle will increase by 2 pi. Of course, if it's sitting on the outside here, it won't increase by that. So if it's sitting on the outside, if we start here, then this one has started with this angle. So that's the angle it will start at. And then maybe it gets to a point here and then another point there. Then this one's angle will go up to that value. And then the lowest it will come down to is here. So it will do that. And you can see here the angle of something on the outside will only change inside of a certain range. It won't go through an entire 2 pi, okay? So the point must be inside the contour. As we travel around this contour, and again, it's an arbitrary contour, we just chose some arbitrary contour. So as long as, while we travel around the contour, anything outside of that contour will change in its angle by some amount, but not by 2 pi. Okay, so let's just get rid of that outside point, right? But all the points inside, if we look at what happens near that point or what happens to that part, it will increase by 2 pi. And the result will be that if it's a 0, g will increase by 2 pi, and if it's a pole, g will decrease by 2 pi as we travel around the whole contour. So every 0 of g in C will increase the angle by 2 pi when we travel around C, and every pole of g in the contour will decrease the angle of g by 2 pi. So, and that's as we travel around C. Okay, are there any questions or comments on that? And what that tells us is that if we want to know the balance of poles and zeros within a certain region, then we can draw a contour around that region, move around that contour, and observe what happens to G as we do that. In other words, and you see it's stated quite neatly, not in my sort of draw everything and talk about everything. It's stated so nice and compactly here. It's saying that the number of times you encircle the origin, right? The number of times G encircles the origin will equal the number of zeros minus the number of poles, right? So that's inside C. So once more, we can pick some arbitrary contour. So let's say we pick a contour here instead. And now we don't know how many zeros and poles there are inside here. Let's pretend we don't know how many are here. So we just pick a contour here, and then we observe what happens with G. So if as we travel around here, so we are going through all these values, and as we travel around here, if we find G does something like this, let's say G does 1, 2, 3, and let's say it stops there, right? Then G has encircled the origin 3 times here. And so we can say that inside of this space on the S-plane, that yes, we have a certain number of zeros. We don't know exactly the absolute number of zeros, but let's say we have 2 zeros, then we must have 3 poles. Not 3 poles. We went around 3 times, so it needs to be, we need more zeros. We definitely have more zeros than poles. So let's say we have 5 zeros. Then because we've gone around 3 times, then it must be 5 minus 3, which is 2. So there must be 2 poles in here as well. So that's what we can say. We can't say how many zeros and how many poles we have, but we can say the difference between the number of zeros and the number of poles, that must be 3. because when we were watching G, as we were moving around this contour, we watched G and we saw G went around 3 times. It's encircled the origin 3 times here. So the difference between the number of zeros and the number of poles has to be 3. So see how clever that is, right? Now we have a way to estimate the number of zeros, the difference between the number of zeros and the number of poles. And we do that just by observing G. And as you saw earlier, we can get some information about G by simple experiments. And it turns out the experiment we looked at with the sine wave, that just gave us for G equals I omega, but that's fine. So if we can somehow watch what G is doing somewhere, that can tell us something about the number of poles and zeros inside of this specific contour. Okay, any questions or comments there? Okay, so that's one piece of logic, right? So the principle of the argument, that's an important step for us. Then the other thing that we want to add to this is, well, the number of poles for an inherently stable process is 0. So zooming out a bit here. For an inherently stable process, the number of poles, number of poles, and I guess we use n for that. The number, well, it gets a bit confusing because now we have z and p. So let's stick with p. The number of poles p equals 0. Right. So so if the process is already stable, then the number of poles is 0. And of course, that's in the right-hand plane, So we don't want any poles in the right-hand plane, because that means we'll have a positive real part in our time constant and it goes off to infinity. So if it's inherently stable, we don't have any poles in the right-hand plane. So if we are thinking about the entire right-hand plane, that's our worry, right? Is our control going to cause us to have instability? So remember, our closed loop function, it looks like this. So our closed loop function, it's equal to G open loop divided by 1 plus G open loop, where G open loop is equal to Y times U. So when we said inherently stable process, by that we mean the Y part, right? So we are saying Y itself doesn't have any poles in the right-hand plane. And we are putting in U. So we are worried about messing this up. We know we are going to put control in, and we are worried that we will cause a stable process to go unstable. So that's the thing that we are trying to figure out now. Is there a way for us to tell when we are causing the process to go unstable? So if it's inherently stable, then this part is not going to have any poles in the right-hand plane. And when we say right-hand plane, we are talking about this, right? So the right-hand plane, a lot of stuff we've drawn here. Let's see if we can just undo all this. Not without undoing that. Well, it's okay, actually. We don't need that anymore. We've gone through the principle of the argument. So I'm just wanting this G plane here. So on this G plane, we want to see how can we look at the entire right-hand plane. So the way we look at the entire right-hand plane is to pick a starting point. So let's say we start on this blue dot here. And then let's say we travel straight up from this blue dot. and we go off to infinity. So that's one part. So we are going off to infinity here. And to emphasize that, we should draw that. So that's one line. The next thing we'll do is imagine ourselves on an infinite semicircle. So imagine now a circle, a semicircle that starts here. So wherever this line is going off to infinity on, we now start drawing a semicircle that goes around here. So it goes around, and it reaches the negative axis here. And then we close the contour. So now we say, okay, from that infinite semicircle, let's go back home, which is here, right? So we come back to the origin here, and we close that off. So this one is going up here. So this is now a contour of interest to us. We started at the origin at 0 here, and we traveled all the way off to infinity. And as we tended to infinity, we said, well, we're at infinity, let's go home now. But we went all the way around infinity, or half of infinity, if you like, because we're not interested in the left-hand side. And then we said, right, we've hit the axis here. We're not bothered about negative real numbers. So let's go back home. So we went there. So would you agree this covers the entire right-hand plane? This is a contour, and we have to imagine a little bit where this contour, we have to pretend we know where this line fits, because it's off at infinity, but still accepting that we can imagine things, and we are dealing with things called imaginary numbers and all that. So we accept we can imagine this. So this is our contour that's going around the entire right-hand plane now. Any questions or comments there? Right, so that's the whole right-hand plane that this contour is enclosing. And you see where we're going now with this, that we now have defined a contour, and our worry is that there is a pole sitting somewhere in this right-hand plane. And, and so we would like to know, is there any, well, number one, we are saying that the process itself is not contributing a pole, but we are worried that we've brought in a pole here. We've caused it to go unstable. So, so that's the next piece in the logic, that we can imagine our way around the entire right-hand plane. So if the process is open loop stable, right, then we know that the process itself doesn't have a pole there. But what we are interested in is a 0 in 1 plus the open loop part. So we want to know, does this go to 0? So are there zeros? Are there zeros of 1 plus g open loop in the right-hand plane? And so we've just said that there are no poles here, right? When we set out, we don't have any poles here, so we know p equals 0. And so what we have left over then is that, and so we had this as well. We said here that this statement eventually leads us to that n, the number of encirclements, equals z minus p. Well, now we've said that p equals 0. So p equals 0. And so that can only leave us with that n equals z. So this gives us a nice criteria now. It's telling us that if we want to know whether we have any zeros in the right-hand plane, then all we need to do is plot 1 plus g open loop. So observing the encirclements by G by 1 plus G open loop of the origin, so of 0, 0. Yeah. The number of such encirclements and the number of those encirclements is n. The number of such encirclements n will equal the number of zeros in the contour if observing that the number of encirclements will equal the number of zeros in the contour. Yeah, okay, so that's generally true. So if the contour encircles the entire right-hand plane, then this is the number of zeros in the right-hand plane. Right, so that gives us a method now. It's telling us just go around the whole right-hand plane, no problem. And if when you observe what this function is doing, and if that goes around the origin even one time, then that means you have a zero and your process is unstable. So once more, let's draw that out for ourselves. So we are saying here, in fact, it's the S plane. So we are doing this on the S plane. So we are going to travel around the entire S plane and observe what G does. So we don't need this stuff anymore. So we are going to do this. We'll start down here. Well, you know this whole story, right? It's drawn on the right-hand side there. You go all the way out here to infinity, you travel around, and let's see if we can be clever with these little thingies. Okay, so it can travel around the semicircle there, and then we come back home. So that's in the S plane, how we travel around the entire right-hand side. Yeah. So this is on the S side. Yes, plane. And then we observe what's happening in the G plane. So the G plane, it's fine if G kind of just faffs around a bit and it stops here. So let's say the starting point was here, and so maybe we started here and we ended here, right? And those 2 points must come together. So if G did that, there's no issue. We're fine with that. That means the number of encirclements is 0. That means there are no zeros in the right-hand plane. If G does this, for example, if it goes around 0, goes all the way around, and then let's say just for fun, it does it again, then that means we have 2 zeros in the right-hand plane. Somewhere there are 2 zeros here. And remember, this G plane, this is for the function, this is for the function 1 plus G open loop, okay? So it means 1 plus G open loop has 2 zeros in the right-hand plane. That's what that means. So if that's the case, then we know that means there are 2 poles in the closed loop case, and so it would be unstable. So that's a method we have now. We construct this right-hand plane contour, and we observe G, and we just count the number of encirclements of the origin. And we can neaten this up a bit. We can say, well, instead of looking at 1 plus G encircling, so instead of 1 plus G open loop encircling 0, 0, let's look at G open loop encircling -1, 0. Would you agree that's the same thing? Right, so if 1 plus G open loop encircles 0, 0, then G encircles -1, 0, right? So, you know, we don't want to have to go and add the 1. We're that lazy. We don't want to add 1. And so we can just say, well, don't worry about the origin, worry about -1, 0. And that's what we do, right? We travel around this contour and we observe G not at the origin, but at -1, 0. So let's undo all that. Oh, can't do it. Anyway, I could just say here, this is -1. Heck. Okay, and here's my 0, 0, 0, 0 is here. So we just look to see, does G encircle -1, 0? That's actually not a good drawing for that. So let's just redraw this. So all we need to do is take our points. So we choose this. Let's put it in nice red because, yeah, that's our danger point. Why are the colors doing this? Okay, anyway, so -1, 0. That's what we are looking out for. And that's basically what we'll do now. We'll be looking to see, we have a way of plotting this right-hand plane. So we'll look at G. If G does this, it's actually fine. It's only when G does this that we say, well, we've gone unstable now. So it might well be the case that this is a specific KP, our controller. Remember, I know we've gone far into this, but by the end of the day, we are still tuning a controller. Feels a bit like we're doing something crazy, but we are still just trying to find a controller. So, when we apply a certain KP value, we observe G. And when we find G only doing this and not encircling -1, 0, then we know we're fine, this controller is fine. But if our controller causes us to encircle -1, 0, then we have caused a pole to exist in the right-hand plane. So this is going to be our indicator of a failed controller. Okay, any questions or comments there? And I must say, there are lots of little pieces of logic that need to be stuck together. And we'll try and summarize it like we did before. We made those 4 points of the logic steps. So we'll come back and do that at some point. So that's our criteria now. And then you're saying, well, that's all well and good, but now you want me to go around the entire right-hand plane with S values. And in fact, we'll be clever there also. And we have said S, that contour can be broken down into 3 pieces. So here's piece 1, and then here's piece 2, right, when we move around on that circle. And then piece 3 is here, when we go from infinity back home. So those are the 3 parts to the contour. Right, we can identify those 3 parts to the contour. Now, the first part we've already done. And I claim that because look at this line here. What would you write this line as? What equation describes this line? Does the equation for this line look at all familiar to you? Does anyone want to answer there? Note takers. So see, on Zoom, it's quite discreet. You have to put your hand up or not put your hand up. Whereas in class, like I normally get somebody kind of whispering something and then we're able to get there. But if you look at this line is nothing but, if we write it here, this line is the same as saying S equals I omega. Right, I'll just use a W there. And that was the line. Remember, all this time we said, well, magnitude ratio, it's nice, we can measure it, but it's only giving us G of I omega. Or I could say it as S equals I omega. G of I omega is the same as G of S equals I omega. And now we have that line. We can see here that moving along this line is basically the same as this. In other words, we can measure the response G for different values of omega. So you can think about that experiment. Where's my little? Remember, we've got our process here. We've got our input point here. And we are using a sine wave here. And we've chosen a certain frequency. If we use a frequency of 0, of course, it's just a constant. If we use a certain other frequency, then you get this line. So this is 0. Let's call this omega 1. And then if we use a higher frequency, so something like that, then that's omega 2. And so as we use higher and higher frequencies, right, and let's say we use a really high frequency here, then we are basically, there's frequency 0, there's omega 1, omega 2. So as we use higher frequencies, we are basically actually measuring G, right? Because we can get a number here, we can get a magnitude ratio. So we can get the value of G as we use higher frequencies. So we can actually directly measure values for G as we move up around here. So that's one thing. We can say at least we can get G values for here. And then the other thing is, and by the way, it's not just the magnitude. I've said magnitude ratio here, but also we've got the phase angle. So remember the phase angle, that was the phase shift that you get between the two. So we can get both those. That's the argument of G, right? So the basic theorem gives us this. So we know everything there is to know about G just by raising the frequency in that nice experiment. Then now, how do we work with this big semicircle here? Well, if you think about this, this is basically the semicircle where S is going off to infinity. So S, the magnitude at least, is going to infinity. And we have said that this process is inherently stable. So generally speaking, we have a whole bunch of zeros and a whole bunch of poles. So S minus N. This is going to S minus N. And what's also known is that if you have more zeros than poles, then you are going to get unstable behavior, that your process, remember this is of the process, your process will be unstable if you have more zeros than poles. So you can look up the inverse Laplace transform of the zeros. And yeah, so if you have more zeros than poles, then as S goes to infinity, the numerator will grow faster. And so that goes off to infinity. So if we have restricted our attention to inherently stable processes, then it can never be the case that we have more zeros than poles. So if that is true, then it's also true that for S going to infinity, for the magnitude of S going to infinity, then the magnitude of G will go to 0. And that's because the number of poles must be more than the number of zeros. So you must have a bigger denominator. So this value will outgrow the numerator. Your denominator will get bigger faster than your numerator. So as s goes to infinity, the denominator will be infinite in comparison with the numerator. And so g goes to 0. So if g is going to 0, then we don't have to worry about that, right? Remember what we were worried about was the g function going and cutting across this -1, 0 point. Now we are saying, well, if you look at just this s going around here part, if you just look at that, then g is going to sit and turn around here and turn around. It can turn around here as much as it wants, but it's not going to go near -1, 0. So that's fine. Then that tells us that we actually don't even need to bother going around here, right? The only possibility was here, that over here we could have ended up going close to -1, 0. When we are out at infinity, g is going to fall into itself. It's going to be very close to 0. So there's no possibility that on this infinite semicircle that we will go close to -1, 0. So we don't need to bother going around this. This is just it's always going to be away from -1, 0. So we don't even bother going around there. And then the last piece we've got is this part here. And of course, this part is nothing but the complex conjugate of the first part. So we've already gone from 0 to I omega, where omega is going to infinity. And so we expect that the complex conjugate, if this one is the s equals I omega line, then the s equals I omega, s equals minus I omega line is going to be practically the same thing. It's going to do this. And so that's symmetrical, right? The complex conjugate has as its axis of symmetry this line. So if that's an axis of symmetry, and if our -1, 0 point is sitting here, then both those contours are, the danger of crossing -1, 0 needs only be checked by one of those. So, and yeah, my bad drawing, it's, let's see if we can draw it a bit better so that it's more obvious. So let's use that little curvy thing. So here to here, you've got that's no, that's the wrong way around. Here to here, let's pull this part first. Okay, so that's what you'll have for that first part, and then for the second part, oops. So continuing the same line, and we drew this side a bit bigger, right? And we should have, it's actually here to here. Oh, no. So the complex conjugate will look like this, right? So this red line and this purple line, KP1, those are complex conjugates. You can see they are symmetrical about this pale blue line. So they will both intersect at the same point here, right? So the key point for us is this one, the place where they intersect most closely with here. And so we can see that it's not going to give us new information about the possibility of encirclement. So if this line s equals I omega, if it does encircle -1, 0, then the red line will also encircle -1, 0. So we don't get new information from this third piece. So we don't have to bother with this part either. All we need is s equals I omega. And we know how to get G for S equals I omega. All we have to do is that experiment with the sine waves, right? This one. So as it turns out, what we do is apply a series of sine waves. We measure the response, we'll get the magnitude ratio and the angle, and then we can plot them. We can use the polar coordinates. We can just plot those points out, and that basically tells us whether G will encircle -1, 0 or not. Okay, any questions or comments on that? So we could just summarize that. Can get G of I omega from frequency experiments, right? So by that we mean U equals U naught sine of omega t, and we just let that omega vary, and that will give us G of I omega. And we'll get it in two parts, magnitude ratio and phase angle. But that gives us magnitude and angle. And so just putting it together, then we'll get the complex number G of I omega. Right, so we get G of I omega from the frequency experiment. If it encircles -1, 0, then unstable. So all we need to do now, and it's bringing us back to our real world here, all we need to do is in our experiment, we apply the sine waves and we can try different KP values. So for our controller, we apply different controller settings and we can see where that intersection moves. So that intersection, when it starts to just touch here, then we know we are going close to instability. So we could think of that as a constraint. We don't want our control variables to go to cause us to go past that point. Right, so that's our criterion there. All right, any questions or comments there? So, and I must say, isn't that clever, right? I wish I had thought of this, but yeah, thumbs up. Don't you think that's clever? No, nobody thinks it's clever. Okay, there we go. Thank you. So, and as I say, I know there are lots of pieces to stick together, but maybe let's try and do that. So, well, I guess we kind of started doing that here. So let's put that in. So number one is the basic theorem. From frequency experiments can get G of I omega, and we didn't know what to do with that. Then the second part is principle of the argument. That tells us that n equals z minus p. Number three is that inherently stable, and that's referring to the process itself. If it's inherently stable, then P in right-hand plane equals 0. Then the other piece was right-hand plane, 3 pieces, only needs S equals I omega piece. And we should mention Y over here. So S tending to infinity, G equals 0 for G for G stable, and S equals minus I omega, that's just the complex conjugate. Conjugate symmetry, so we don't get new information. We don't get more encirclements. Yeah. Is there anything? Then I guess we could add this last piece here. So that just summarizes it. So we had those first four ones as well. Remember about the, so just stick this on to the end. And so those 9 points are the entirety of the logic of the second half of the course. So if you can understand each of those steps, then you understand everything there is to know in this part of the course. And each of those steps can be derived. We have derived each of those steps from first principles, or some of those are not even real derivations. Some of those are just observations. And those are things you can agree with. If you don't agree with it, then you can tell us and we can try and work it out in class, okay? Okay, so work through all 9 pieces of logic, see, and we can talk further from there. Then with the rest of our time today, let's actually talk about how to use this now. Let's look at some nice problems. Okay, so that takes us back here now, when we said we're going to skip past all this stuff on drawing the diagrams. Yeah. Okay, so one of the things we'll do is use a Bode diagram. So a Bode diagram, so what follows now, these are all just ways to look at the things we've been talking about there. So there's 9 pieces of logic. That's actually everything we need to know. And now we just have ways of drawing things a bit differently so that we can see where we are, how closely do we encircle -1, 0, all that stuff. So it's now just about visualizing it. So even though the textbooks quite emphasize this, and the majority of the textbook is how to draw these things, it's actually just, and today with computers, you don't even need to do that much, but we'll do it because in your exams, that's, I guess, how you have to answer it. So the log modulus is defined this way. Well, this is the log modulus part. So the Bode diagram is both these things. So in the log modulus, we are trying to get away from this magnitude. So this G of I omega, which it can be a bit of a complicated thing to work with. When we put it in this form, it suddenly turns out to be much, much easier to draw G of I omega. And let's see that here. So the first one is already easy enough, so there's not much to see here. But if G is just a constant, if it's not a function of S, if it's just a constant, then the magnitude of G is actually the magnitude GP, sorry, it's the magnitude of KP, which is just KP because KP is positive anyway. And so L looks like this. So it's the log of this constant. Sorry, I need to just get my throat in order. 1 second. So sorry if you hear me crunching a sweet in the background, okay? So here, yeah, your KP, so for each chosen value of KP, there's a fixed value of L. And so it doesn't matter what your omega is, L is not going to change here. So yeah, I forgot to say, on these Bode diagrams, we have as the X value, the omega. So omega is here. And you can see it's not a function of omega. So that's just a constant that looks like that. So that's the magnitude. And then also, because this is a pure real number, then you can imagine the angle is also just zero. So the angle is zero always. This is a pure real number. Theta will always be zero then. And so we just get a boring zero here. So for a simple function like this, that's what it looks like. Here's something a little bit more interesting. And we call it a first order lag. I don't think we used that terminology before, but that's because if you look at this equation, that's something like the solution to that is something like 1 minus e to the minus t over tau. Oops. E to the minus t over tau. So it's like an exponential decay. And so that's what we have here. So now let's see how to develop the Bode diagram for this case. Sorry, 1 second while I crunch this thing. Okay, sorry about that. So here's our G function, and we want to get the magnitude ratio here. So let's do it from scratch. So G is 1 over, why am I bold here? G equals 1 over 1 plus tau s. And so G of I omega is going to be, right, so Bode diagram is specifically for S equals I omega, right? So G of I omega is going to be this. And we want to get that out of the denominator. We don't want an imaginary number in the denominator. So we will multiply by the complex conjugates. Top and bottom by the complex conjugates. And so we know that we will get we're going to get plus tau squared omega squared without the I. Right, so if you look at this, you can see here, you're going to get 1 times 1 plus minus tau I omega plus tau I omega, so they'll both cancel, plus minus tau squared I squared omega squared. And I squared is minus 1, cancels with the other minus, leaving us with 1 plus tau squared omega squared. Okay, so multiplying complex conjugates does that. So now we have a nicely separated real part and the imaginary part. And so we can say that the magnitude of G of I omega is equal to, and it's going to be the square root of the real part squared plus the imaginary part squared. So that's nothing but 1 over, well, let's just steal it from here. Is that, so this is the real part, and then I guess we have to square that. And then the imaginary part squared is also the imaginary part is this here. Right, so that and that. And just trying to see if we can simplify this. Got one squared. Okay, so this looks like, and when we square this, we'll get tau squared omega squared, and the -1 vanishes. So we've got minus tau squared, tau squared omega squared. So that's just getting rid of. That's just bringing the two together. Right, so once more, we've said 1 squared, so the square here, 1 squared plus minus tau omega squared, so this should be a plus here. And then we have to square the denominator as well. So we can rewrite that with the denominator squared. And you can see the numerator and the denominator have the same form. It's just the denominator is squared. So this can be rewritten as 1 over this stuff. Okay, so that's our g of I omega, the magnitude of g of I omega. And then what we can do is say what we actually want is L, which is 20 times log base 10 of g of I omega, which is equal to, so the magnitude of g of I omega we've just worked out here. So it's all this stuff. And we could rewrite this also. We could say this is actually the same as, and we can take this and we can see we are inverting it and square rooting it. So we can rewrite this as this thing raised to the power minus half. You agree with that? Okay, and so that's our L. Just wanting to summarize it, but well, there's one more thing we can do. So there's L here, so that's L, yeah. And now it's log 10 of something raised to the power here. So this raised to the power stuff, we can, because it's log 10, we can bring it to the front and rewrite this as minus 10. In other words, minus a half times 20 is minus 10. Yes, I have to do this. Okay, so that's our equation for L, which is all well and good, but the nice thing about this is how easy it is to draw. So we can say here, for low omega, we can see that L is approximately the same as, so if omega is really small, then it will be small with respect to the 1. And that leaves us with minus 10 times log 10 of 1. And as we know, the log of 1 is 0. So it's 0. So that gives us a lower asymptote. And then for large omega, L is approximately equal to, and you can see when omega is very large, then 1 is small in comparison. So we can forget about the 1. And then we can identify this as tau omega all squared. So we can take the square out here and just write this as tau omega. And then that 2 we can multiply by the -10 as well. So that's equal to tau omega. To tau omega times -20. And now we know that the x-axis is log of omega. So we'd like to separate this further. So we've got the log of a product. So we can rewrite this as -20 times log tau. And then it will be -20. I'll get rid of this stupid thing. I'm just going to keep it, okay? -20 times log of omega. So this tells us then that for low omega, so let's actually draw it. So here, let's clear up. So let's take 0 up here. Do a bit of labeling. So this is L, and there's 0. And this is log of omega. Log omega. And for low values of omega, L is approximately 0. So we can say L starts out here. And then there comes a point where L, so remember the x-axis is log omega. So you can say L is equal to, so this part is a constant, right? Tau is a constant in our equation. So let's just call that some constant K eventually. And then -20 times, and this is the x-axis. So we are plotting against log of omega. So we can think of that as our x, So that's the equation for L for high values of omega. And I'm writing it that way because now we can see the gradient here is -20. So all we need to do is draw a line of with the gradient of -20. So it will look like that, something like that. So for high enough values of omega, that's what we get. And we can use this little curvy thing. It's quite handy. Ooh. Yeah, wasting our time now. Not much better, but anyway, but you can do this better than me. Okay, so that's what our L part will look like. It's 0 initially, or for low values of omega, and it has a fixed slope -20 for higher values. And we can also figure out where it starts to depart. So if you were to extend this line back a bit, so let's just draw this here. So if you extend this line back, we need to know where it starts curving out and becoming that -20. So we need to know this point right here. And we can easily find it. We can say when L equals 0, then there's a certain value here. And it turns out that this value, in fact, if you just look at this, when L equals 0, then these two must balance. So these two will balance. In other words, these two will be equal to 0, equals 0, when omega is 1 over tau. Maybe another way to say that. Okay, let's see. When omega is 1 over tau, no, when omega is 1 over tau, then you can see that 1 over tau will equal, so this is tau raised to the power -1. So we can make this tau here, and then this will be a plus because we get a -1 from that, right? And now you can see these two are equal and opposite in sign. So now we are equal to 0. So for the value of omega equals 1 over tau, we get the 0. So this line has that equation. Remember, all of this was under the approximation that gave us the straight line. So we looked back along the straight line for the 0, and we found the 0 is when omega equals 1 over tau. So we can just look up omega equals 1 over tau, take the log of that, and then that defines that point there. And that's why these Bode diagrams are so popular and so easy to use. Most of the time, you start from 0. You just need to work out 1 over tau. That gives you a point here. And then you work out whether your gradient is -20 or -10 or something. And yeah, if you have a form like this, then it will turn out to be -20. If it's squared, then it's -40, and so on. And we'll see that for more examples like that. So the Bode diagram is extremely easy to use. Just by inspecting the form for G, we can pick out enough features that we can rapidly draw these diagrams. So that's how we draw the L parts. And then, of course, there's an omega part to draw as well. But let's keep going with the L part. So if you have an equation with a different form, let's say you have 1 plus tau 1 s and 1 plus tau 2 s. Then, as before, when you eventually take the log of this, you'll be able to separate that out into different terms. So do this as an exercise, right? Go through all these steps, but you'll eventually get that you can separate your L into the sum of these different parts. So you'll get something like L equals, this is for that other, for the denominator. You'll get that it's equal to this minus, and you'll have a tau 2 over here and a tau 1 over there. And so when you add these together, and you can do the usual thing, move the 2's out, and so it's 20. And what you'll be able to say then is, well, the other one only kicks in. So let's say tau 2 is sitting somewhere here. So let's say tau 2 is there. Then this line will also have a gradient of -20. And so the net result is that the Bode diagram, it's going to be 0 up to this point. Then it starts to get the contribution from the first part. So it will have a slope of -20. Then at this part, you'll be adding another -20 to it. So the result of that will be that it will drop faster. So the gradient will go from -20 to -40. So it's like that. So that's the beauty of these Bode diagrams, that your function can be as complicated as you like. And maybe you have terms up here as well. So if you have a 1 plus tau 3 s tau 3, yes, then do this as an exercise, right? Do first g equals just 1 plus 10s, right? Draw the Bode diagram for that. And in the notes here, you'll see for that case, for that case, it looks like this. It's also has, it's close to 0 at low values, and it eventually has a gradient of 20. And we say that as decibels per decade. So per decade, because it's per 10, right? Remember, this is the log 10 scale. So for each increment here, it's a factor of 10 for omega. So 20 decibels per decade of omega. So in the case of S plus tau omega, it's a plus 20. For the case of minus, then it's, I guess, let's just look here, then it slopes down. So if it's 1 over S plus tau omega, it slopes down -20. For G equals 1, for G equals S plus tau omega, not 1 over, then it slopes up. So there's a really nice symmetry like that. In terms of the theory, there's a symmetry. So even if you have a complicated case with things in the numerator and denominator and so on, all it will do is just add another term here. So it will be a plus 10, the same stuff, right? It will be with a tau 3 instead. So if you had that in this case, if you're, let's extend this a little bit. So if you had a tau 3, let's say here, so let's say there was a tau 3, oops. Let's say there was a tau 3 right here. Then that part we would draw like this. So we would say, well, that one is 0 up till 1 over tau 3. And then at that point, it will start increasing this way with the 20 decibels per decade. So then when you are adding all these together, it's 0 initially, then the first part comes in, the part with the tau 1 comes in, then the tau 2 comes in. And now we will also need to add in, at this point, this contribution. And this effect is to shift it back up. So we were going down at a gradient of -40. And then when we get this contribution, it goes back to -20. So it goes back to being parallel to the first one. So that's how beautifully simple it is to draw it with the Bode diagrams. You just look up the time constant for each term here, and that defines the crossover. And then you can sketch that individual part. You can say before the crossover, it's 0. After the crossover, depending on whether it's in the numerator or the denominator, it will slope up or slope down at a gradient of 20. And then that gives you all the pieces. And then you just have to add the lines together like that. It's as easy as that. And I guess we're out of time now. But for the angle, it's similarly simple. So we can talk about that next time. But for the last tutorial that you had, we had all those functions defined. So for the tutorial for today, please go ahead and draw the Bode diagrams, at least the L part, for those cases that were defined there. Okay, any questions or comments on any of that? Okay, if not, I guess that's it for today. See you next time.